So here, how can we design the RC high pass filter or RNC based high pass filter? You remember the LPF, low pass filter? The design is like this. The resistor is here, and then we are putting the capacitor and then getting the output across the capacitor. That is the low pass. In the high pass, we are just interchanging these two elements. Capacitor is going here, resistor is coming here. Just change the position of the two elements, then you will get the high pass filter. Very simple. So we just interchange the position of R and C, then it will become, so you interchange the position of R and C in LPF, then it will become high pass filter. So here, how this high pass filter is working, we know high pass filter is only passing high frequencies and blocking the low frequencies. So at very high frequencies, the capacitive reactance becomes zero. The same principle what I told in the low pass filter. So it means the output voltage is same as that of the input voltage. So that is V out is equal to V in. But the opposite at the low frequencies. At low frequencies, the capacitive reactance value is infinity. It's very high. So thus the output voltage is zero. So remember, I am talking about the reactance value and then the output with respect to frequency. But here the position of the capacitor is in a different place. It's not in the same location. That is why this design is acting as a high pass filter. So this one is performing the opposite operation. So it's passing the high frequencies and blocking the low frequencies. So if you just read this definition, you will understand what does it mean, and you can compare with the low pass filter. So the capacitor at low frequencies acts like an open circuit because here it's in series. So at low frequencies, the capacitor is act like an open circuit. So what it means? It means the signal cannot pass through. So it means the output is zero at the low frequencies. Which means that okay, but at the same time, when you increase the frequency, so it means it's high frequencies. At high frequencies, the capacitor will become a short circuit. So it means it will pass the frequencies and you can get the output. That's what mentioned in this paragraph. The capacitor will block the low frequencies entering into the capacitor due to the capacitive reactance of the capacitor. So since the position is here, so it blocks the low frequencies because it acts like an open circuit. At high frequency, so the capacitor charged and it becomes a short circuit. So it passes the signals and you can get the output. It's a very simple logic for the high pass filter, but it's just totally opposite operation of this LPF. By the way, the cutoff frequency formula is same, 1 divided by 2 pi RC. So the cutoff frequency value FC is really depending upon the value of R and C, which you are using in the circuit design. So now we will see the phase and frequency response of the high pass filter. So high pass filter is exactly opposite to low pass filter. So here, until the cutoff frequency, all the low frequency signals are blocked by the capacitor. So it means it's resulting the decrease of the output voltage. So here you can see, so this is the low frequency area. So the capacitor is acting like an open circuit. Of course, this is not ideal one. So the output is not exactly zero, but the slope is increasing or raising slowly. And then after the cutoff frequency, this is just rapidly go up and then you get the output. So it means it passes the high frequency. This is the high frequency region. Okay, so after FC, if you still increase the frequency, yes, after FC, I am increasing the frequency of the input signal, the output will increase to the maximum at the rate of minus 20 dB per decade. and also phase will get changed. So this is the phase. So here are the formulas. Okay, before that, so this is called a stop band, where we are blocking the low frequencies, and this is called pass band, where we are passing the frequencies. And here also we have the 0 dB and minus 3 dB level. So after the minus 3 dB, then it start to reach the maximum value of the output very soon, because this is what we want. At high frequencies, we want the output. And okay, here are the formulas. Try to remember cutoff frequency or breakpoint. That is the breakpoint actually. So from here, there is a rapid change. FC is equal to 1 divided by 2 pi RC. Sorry, this is 2 pi RC cutoff frequency. And phase shift pi is equal to tan inverse 2 pi f RC. 2 pi f is nothing but omega RC. And the formula is also kind of similar as the low pass filter. And this is the output voltage of the simple high pass filter, passive high pass filter. V in times R divided by square root of R square plus XC square. So please remember, the formula for the low pass, passive low pass filter is different. So this is the output voltage of the passive high pass filter. Please write it down, this also in your notebook. So later it will help you to make a summary. And what is the voltage gain of this high pass filter? V out divided by V in. This is the formula. So R divided by square root of R square plus XC square. So if you consider this as an impedance, then R divided by Z. But just remember, this is the formula for gain of this passive high pass filter. Okay, so here we had seen few formulas. So now I think this is not the low pass, this is the high pass. I forgot to change the name. Okay, so the high pass filter, we have to find the FC cutoff frequency value. We know how the circuit design is. C is here, R is here, and we are getting the V out across the R resistor. So here the capacitor value is 82 picofarad, resistor value is 240 kilo ohms. So how can you find the cutoff frequency? It's very simple. FC is equal to 1 divided by 2 pi RC. Just apply the value and you will get this value.